All right, I guess it's time to start. Welcome. This is Co-17A, not Co-19A or Co-16A, even though it says Co-16A on schedule folder. So hopefully you're all enrolled in a Math 17A class, specifically not in section B. So if you're thinking 17A with Dr. Diddell, hopefully that's not true. But if it is, you should be in the other Co-17A class that meets in the morning on Tuesday and Thursday. Hopefully, all of you are either taking Math 17A with Professor Lewis or Varn or Alameda. I believe those are the three other instructors. That sound right? Is anyone here in Dr. Diddell's class? Cool. Good. And just the reason is because he's extra. He does extra things that not everyone else does. And so you shouldn't have to be forced to see me talk about that for his students. So we have two separate co-classes and we try to keep the students in Diddell's class separate from the students in the other classes. That said, most of the content I'll talk about in the morning class and the afternoon class will be pretty much the same. Most classes, occasionally there'll be stuff I do in that class that I won't do here. Cool. I should introduce myself. I am James. I am the teacher for this co-class. Do make sure that when you get the chance, when the sign-in sheet comes to you, just write your name in there. Ooh, ow. I mean, it didn't really hurt. You need to say ow and hit yourself. But what do you need to know about me? My name is James. I would prefer to be called James, but if that's not comfortable, you can call me teacher or instructor, or I'm not a professor, but you can say professor if you like, or you can call me Mr. Parmenter, which sounds like a lot to say. Yeah. You're always welcome to ask questions or say things or point out mistakes I've made. I guess we should go through the Canvas briefly so that everyone is on the same page and understands how things work. There's not a lot to this class. Most of this class is going to be me showing you things or me having you work on problems together or on your own. And then making sure you fill out the attendance form or you fill out the attendance thing and do the weekly reflections. That's like, we'll talk about it all more in length and depth just because we should, but that's really it. Like, come to class, learn the math, fill out the attendance form, do the weekly reflections. To be a little more specific, some of you enrolled in the class with a CRN. Some of you got added to the Canvas because you filled out a Google form. Both are fine. For those of you that enrolled in the CRN, you have to do the things. That's not true. You don't have to do them, but if you don't do them, then you won't get a unit for taking the class. Is that really a big deal? No. It'll show up as a no pass on your transcript. Does anyone care? No. Like, to be really frank, nobody's looking at your transcript in the future. Those will be like, oh, they graduated from UC Davis with a 3.8, but they got a no pass on the transcript. The world's looking at nobody cares. But you still want to pass the class, and everyone can pass the class. So if you're enrolled in the class because you use the CRN on Schedule Builder, you should definitely make sure you do the things. Come to class, fill out the attendance form, do the reflections. For the rest of you that did not enroll that way, who are enrolled or got added to Canvas using the Google form, you should still do the things too. You don't have to do the things. Your grade on Canvas doesn't matter at all, but you can still come to class, fill out the attendance form. I really would like you all to fill out the attendance form whenever you come to class, or the other attendance form, which I'll show you in a minute, if you come to class virtually via Zoom or watch the recording later, because we keep track of the students we serve. It's important to keep track of those numbers, but it is not vital for your own selves that you do that. But do it for me, if you like. I know we just met, but so those are the things, right? Oh, and the reflections are nice to do. They're really good to do, and we'll kind of get there in a second, because it's an opportunity. It's one opportunity for you to tell me what you would like to see us do in class for next week. So if you have things like, I'd really like to talk about limits or derivatives or the quotient rule or something, you can say that there, and then I'll be like, oh, great, I have an idea of what we would like to talk about next week. Let's go ahead and look at Canvas. Something I like to show everybody about Canvas is that for your class, this class here, you can change things. You can change the color of it if you would like to. You can also change the nickname. Maybe I just want to have something else in there instead of Tuesday. I like to write the time and the place typically, so I might just change it. I know what time it's at. I know I'm gonna write the places in 3216 Dutton Hall. just so I know where things are when I look at Canvas, because I'm looking at Canvas a lot. So there, look, I changed it. Great. You can change it to whatever you want. Me doing that shouldn't have affected how yours looks. And now let's take a look at it. So here is, there's the recent announcements. Does your grade in Canvas matter? Read that if you're not sure. It matters if you registered with the CRN. It doesn't matter if you got added via the Google form. Okay, that's the last time I'll say it probably. Oh, thanks. If you didn't get this at some point, come up at the end of class and fill it out. Let's go over the syllabus real quick. Most of the time, though, if you're looking at Canvas for this class, you're going to be looking at the modules, or I guess the assignments. I forgot about the assignments last time. Okay, cool. So, well, it looks interesting. I don't have that extra parentheses there. I'm gonna have to fix that later. Here's some of the information. The CRN is that number. You can attend. So if you want to attend via Zoom, probably the easiest way to get there would be to go to Canvas and then click on the Zoom link. That's probably how I would do it. The ways you can reach me, if you need to, you can send me emails, probably best. If you call my office and I happen to be there, I will answer my phone, but I'm not often there. I'm there some of the time. You can also come by my office, but it's kind of the same thing. If I'm there, great. If I'm not there, there. You can find me in my office hours, which are listed here. Let's take a look real quick. These are the times and places. Monday, Wednesday, 11 to noon in math drop-in. That'll be starting not this coming Monday, but the Monday after, October 7th. Drop-in starts the day before that on Sunday, October 6th, from 3 to 7, and then Monday through Thursday from, I believe it's 10 to 5, but I am specifically there 11 to noon on Monday and Wednesday. The rest of the time, it's staffed by student tutors, mostly. Occasionally other specialists like myself or Grant or Jen will be there. We're all lovely people who want to help you with math. And then I also have office hours Monday, Wednesday, Friday from 2 to 4 in C class, which is the Center for Chicanx Latinx Academic Student Success. That is in Memorial Union Room 210. If you've gone to the coffee house, see the flagpole out there, you go up those stairs, they're outside, and then you kind of look to your left and it's right there. It's easy to see. There's a big sign on the window. And thirdly, I have office hours right after this class, actually downstairs from 3:30 to 3:40 to whatever, 3:30, 3:40 to 4:30 in 2258 Dutton Hall. Those are my office hours. That's probably the best place to find me if you want to get math help. Grading for this class, it's pretty straightforward. It's based on attendance, which is 70% of your grade, and doing the reflections, which is 30% of your grade. And you have to get a 75% or higher to pass, which means you need to do at least a couple of the reflections if you're enrolled in the class, right? If you come every day, that's only 70%. The reflections, I think there's 10 of them. They're worth the other 30%, so they're each worth how much? 30% for the total. There's 10 of them. 30 divided by 10. Right. So each reflection is worth 3%. So if you came to class every day, you'd still have to do at least 2 of the reflections to make sure you pass the class. But really, you should do them all because they're easy to do. Let's actually take a look at them. They're really like, they take like 5 minutes, maybe 10 minutes at the most. Here are the reflections. Yeah, sure. Down, scroll down, down, down. Reflection. Oh, that's like reflection number 2, actually. Like, reflection number 1 is some just like what your name is, what you like to be called, where you're from. I think I meant to delete question 3, but I forgot to, so it's there. Where would you be from? That, I don't know about that question. Oh, well. Oh, yeah, it might. Okay, anyway. So, yes, there's some questions there. There's no math questions there other than like things about math, but not actually like solve an equation or take a derivative. But let's look at the second one because I feel that one's a little bit more reflective of what's actually going on in the reflections. I'm bad at navigating Canvas sometimes. Let's look at reflection number 2. So this will be pretty much every week the same thing, maybe a little bit different. But I'm just going to ask you, what did you do in your 17A class so that you can think about what you've done and I will know what you have done. I'm also, if your professor is posting them, usually watching their videos or looking at their notes to kind of get an idea of what they've done. It's usually pretty similar over the course of each week. Most of your professors should be in about the same place each week, but people do things slightly different. Sometimes some people, one professor in specific, although he's not teaching it this quarter, does like the sequences stuff at the end of the quarter instead of the beginning of the quarter. But for the most part, everyone should be in pretty much the same place, hopefully. That said, sometimes I might be doing things that you haven't gotten to in your class yet, or that you've already gotten to, and other people haven't gotten to. So there is going to be some kind of push and pull in that way. So what did you do last week in your class? What grade would you give yourself in your class, just to kind of have an idea of how you're feeling about the class? Is there anything you would like to see me cover? That's kind of the most important one, in my opinion, so that I know what you want to talk about next week. And then anything differently I can be doing. I don't think I always ask that question, but it's good to start off with. And then usually some sort of question about something you like, something you're interested in, something you're doing. I don't know. This one is, what is a story that you have really enjoyed? Oh yeah, I like that. I'm thinking about books, but it could be a novel, a graphic novel, a video game, something else. And yeah, that is my current favorite. It's a great book. Actually 3 books. The Last Graduate by Naomi Novak. Excellent read. I highly recommend it. And then very lastly, every time, if you have a joke or a meme or a pun that you want to share with me, I will gladly consume it. All right, that's all I got there. Let's close that. So the reflections, again, you shouldn't spend that much time on it. Like really, like if you spend 10 minutes on it, it's probably too much. And then I will read them and sometimes comment on them depending on how much time I have in my schedule. Let's see, what else? Yep. Okay, so if you attend class not like this, like so if you come via Zoom, which I honestly kind of thought some people might be on via Zoom today, but let me double check one more time. Nope, it's just me on Zoom. Okay. Hopefully they're fine. I'm always worried like maybe they have the wrong link or something. I mean, like, am I getting emails about Zoom? Nope. Okay. Yeah, yesterday I was because it wasn't working. All right. But if you attend via Zoom or watch the recording at a later date, then I would request that you please fill out this form. It's pretty easy. Your email, your UC Davis email preferably, your ID number, your first name as it appears in Canvas. So I would write James. Your last name as it appears in Canvas, I would write Parmenter. And then the class you're here for. I should probably delete the live in person part here because if you're attending live in person, you'll be filling out that form, not this form. What class date are you marking attendance for? So if you are not here today, if you're watching this video and it's say Saturday, September 28th, you should still put in today's date, September 26th for the date because it's the date that the class met, not the date that you are watching it. And then very lastly, oh yeah, no, not very lastly, but along with that, make sure you enter the date correctly and please enter the full 4 digits of the year 2024, not just 24. Otherwise, when I sort things later by date, it won't sort correctly and it's annoying. So please do that for me. I would greatly appreciate it. All right. What else have we got here? I already said not passing is not the end of the world, but everyone can pass, so it should. Things about this class, if there are things impacting your success, don't hesitate to talk to me. Really, this class is pretty chill, but if there are issues, you're welcome to talk to me or someone else, my boss, whatever. Haven't had any problems with that, but I don't want anyone to feel uncomfortable. So if there's something I might accidentally do to make you feel uncomfortable, I'm happy to correct it. I don't anticipate that, but I can't anticipate everything. So please don't hesitate to let me know if I'm doing something that is terrible. Again, I don't anticipate that. Our class is here at this time. Cool. I'm going to show you examples. I'm going to have you guys work on stuff. You're going to work with each other. Come prepared to work on math problems. That means a writing utensil and a thing to write on typically. You shouldn't really need anything else. I mean, you could bring a calculator. You most of the time won't need it. You could bring your book, I guess. That sounds terrible. But I guess I'm down. People you don't care on physical books anymore, right? It's all PDFs typically for the most part. I like a physical book. Do I have it with me? I do. Yes, this is what your book looks like if you have a physical copy of it. Gosh, it's gigantic. More on that later. And then accommodations, if you have accommodations, you might have already let me know. For the most part, the accommodations in this class aren't really meaningful in that we don't have any tests, we don't have any homework. You're welcome to record the class, but I'm also recording it. So anything you want to do, you're welcome to do. but you also probably don't need to. But you, again, welcome to if you need to, or even if you don't need to, if you just want to. What else here? Zoom, yeah, everyone knows that. The Zoom instructions are kind of old. Everyone knows how Zoom works. Some notes about the class. It's worth 1 workload unit. I always try to get people to use the discussion tab in Canvas to talk to each other about math problems. No one ever does it. But if you wanted to, you could. And it's a great place to do it because specifically there, I can respond as well. And I can write in nice mathematical typesetting. So I can make the math look pretty so it's easier to read, as opposed to like the terrible, like in a text where you're like X and then a little caret sign for 2. Like I can make my X squared look nice, not terrible. So if you had math questions and you thought I might respond, which I probably would, if you write them in the discussions, I can write back and write nice mathy looking answers or responses. We'll see. It never happens, but I'm always hopeful. And then let's see, was there anything else in here? Successful students are usually spending 10 to 20 hours per week outside of class doing homework, practice problems, studying, etc. The more you practice and ask questions, the more successful you will be. Finally, where can you get more help? Office hours, as I already mentioned. Grant's website is an excellent resource for all of your calculus needs. Why I need to fix that link. Remember to write myself a note. Fix the link. The Grant's 17A website. It was wrong in my other class too. Okay. But then you can just click here. It'll be just fine. So here's the link to Grant stuff. It's lots of notes on various topics that you cover in class in, I think, a fairly chronological class order. So this is the order that things typically get covered in your 17A class. Lots and lots and lots of stuff there. And then we also have AATC tutoring, which I feel like I've mentioned already. Let me double check while we're here. Here's the tutoring stuff. So you have a couple options. You can schedule an individual appointment with a student tutor using this. I can't really click on it usefully because I'm not a student and it'll ask me for information I don't have. There's drop-in tutoring in the library, which is Monday through Thursday, 10 to 5, not 11. I need to fix that too. Drop-in. How they had it is 10 to 5. And then Sundays 3 to 7. So drop-in tutoring starts not this weekend, but next Sunday, October 6th at 3 to 7 p.m. It's kind of nice that there's something on Sunday because you're like you have something due on Monday and you, yeah. And then there's also, of course, the co-classes, which is where you're at right now. But there's also the calculus room, which is not at all associated with us, but it's another useful resource for getting help with math. It is staffed or run by graduate students in the math department, which I was once upon a time, many, many years ago. Lastly, maybe the best resource you have is each other, classmates. You should study together. Not that you can't study on your own, of course, but really working with each other is kind of where it all comes together. It's certainly where it came together for me as a student, working with other people, coming up with questions to ask other people, thinking about like, they could ask this on the test, is really a lot of where your best learning is going to happen. So please, please, please talk to each other, utilize each other as a resource, study together. It's more fun that way too, right? It's boring if you're by yourself. I mean, I don't know, by yourself is fine, but it's more fun with other people. All right, so before we get into the rest of Canvas, any questions about the syllabus stuff? Yes.
Which calculator would you recommend for calculus? Like a TI-84 good enough?
I like it. Oh yeah, TI-84 is definitely good enough. It's probably the most you would need. I will say most math classes at UC Davis don't permit you to use a calculator during your exams. That doesn't mean it's not a good tool to have. I would say though, as far as graphing, you would also be perfectly well served by using Desmos and getting very I would, regardless of whether or not you have a graphing calculator, I would highly recommend each and every one of you get comfortable using Desmos. Specifically, the 2D version for 17A and 17B, and the 3D version for 17C, because there's wait, what? Yeah, there's some 3D graphing in 17C. So desmos.com/calculator. It is a wonderful tool. It's very powerful. if you ever want to just come and talk to me about using Desmos, I think it's a lot of fun. You can graph all kinds of stuff and do all kinds of, I don't know, there's all kinds of tools. And you can like click on this and make a little table. Oh, and it's especially useful for when we talk about semi-log and log graphing later on. So Desmos, there's a way to do it using Desmos, which is kind of slick. There's probably a better-ish way to do it using Google Sheets, which is also nice. But there's actually instructions on my on Canvas about how to do it both ways, or instructional videos, I should say. But yeah, Desmos is great. Get comfortable using it. TI-84 is a wonderful calculator. If you have one, great. If you don't need to go out and buy one. I don't love the phone calculator. I will definitely, I think I brought a calculator in the class. Did I? Yes, I did. I typically don't bring a graphing calculator because I would just use Desmos to graph things, but this calculator is perfectly acceptable just to do calculations. But the phone one is not my friend. It's just easy to like, I don't know, it feels like you don't enter things correctly and like, yeah. But yes, I like a graphing calculator, big screen, you can see all your work. But you probably, a regular scientific calculator would probably be sufficient, or something on your phone would probably be fine, I guess. Yeah, so I know it's not a really straightforward answer, but it's the answer I've got.
Thank you.
You're welcome. I thought there was something else I was thinking of as I was saying all that. Oh, I know what it was. You can check out a TA84 something plus, I don't know, whatever, TA84 something. Actually, let's find it. So I think, let's see. UC Davis Library. Calculator checkout. Cool. So somewhere down here, talks about how you can borrow things. Yeah, I think it's here, equipment lockers. Yeah, so I'm here already. You can borrow a TI-36X, which is this calculator, and this is the 30XS, sorry, it's pretty much the same as this calculator, or a TI-84 plus CE. I don't know how long you can check them out for, or if you're allowed to leave the library with them, but you know what? The library is a great place to study. So you can go to the library, which is where the drop-in tutoring is downstairs, and borrow a calculator if you don't have one and use it. And I highly recommend it. It's a lovely resource, and I don't think it gets used very often. So I imagine they probably have plenty of libraries to lend out. But yeah, I don't see, you can't click on this. So I don't know exactly how long you can check out a calculator for, but seems worth checking out. Also, I point out there's lots of other things you can borrow too, which is kind of cool. I didn't know you could borrow charging cables and headphones. I don't know about headphones. That seems, but yeah, all kinds of things you can borrow. That's kind of neat. You can borrow a chess set. Cool. Anyway, there you go. Information. Nice. Good to know. Other questions from the syllabus before we get into the module? You're always welcome to ask questions. Well, let's look at the module. So I'd say the syllabus, good to have gone through, but you probably never need to look at it again. And I will probably change the homepage to be the modules because that's where the useful stuff from this class is. Speaking of useful things, there are useful links here. The link to the class attendance form, which you talked about, the link to the Zoom, you can find it here too. My office hours should be mentioned, my playlist on YouTube. So any recordings from this class and actually also the other 17A class I'm teaching will get posted on YouTube. I will also post these class specific ones in Canvas, probably down here. I'll probably put in a new module right there for current class recordings and video and class notes. And then there's also a link to the class notes there, but they'll be down here as well. There's links to everything. Grant's website again. I wonder if this link works. Let's find out. Nope, that one's broken too. Okay, I gotta fix that one too. My website, which is totally not useful at all. You can see a picture of me and my cat and where I am, when I am, and some links that are not useful to 17A. So yeah, there you go. We saw it. Great. It's over. Cool. And then these are actually moderately useful. These are some old video lessons we were putting on our own website back before we started putting everything on YouTube. So the nice thing about the things here is there are videos on pretty much every topic in the syllabus of 17A. And I think most of these videos are relatively short. So unlike the ones I will post, which will be about the entire class length, these ones are like 10, 15 minutes. So if you're looking for shorter content on domain and range or parent graphs and functions or other graphing things or whatever you like, these take a minute to load, but they do eventually load. And you can be like, oh yeah, there's an old one of me. Limits of sequences, all sorts of things. So if you're looking for more content, there's more content. This we'll get to later when we talk about how to determine if a relationship is log or semi-log. And there's a couple. This is a page here. Let's take a look. I think it's just a link to a video of me doing it. Yeah. Yep. Cool. So when you get to the log stuff and the semi-log stuff, you can watch that. We'll also probably talk about it in class, but if you are there before us or you just want to see it again, there it is. I probably need to watch it again to remind myself of how to do it exactly. There's some useful handouts here. Derivative stuff mostly so far. Old class recordings and class notes, which is a lot. Whoa, okay, that's too much. That's why it's not like that. There we go. Some exam prep materials, which I think is empty. Yeah, I can't close it now. It's annoying. And course evaluation, which will be live like the last 2 weeks of class, so that you can give me feedback on how I've done. It is anonymous. My boss gets it and then disseminates the information to me, eventually saying the student said this. Yeah. No, if you're attending live, you are going to fill out this piece of paper here, which not all of you have gotten. So before the end of class, do make sure at the end of class, make sure you come up here and write your name, whatever your name happens to appear. Yes. Other questions?
Do you recommend reading the book and watching the video or watching the video?
I mean, reading the book. Reading the book is hard. Like reading the book, I feel like it's just kind of dense. I would say looking at the examples in the book is maybe good. I don't think I would want to, like, I'm just trying to think about if I was looking at, say, oh, it's just so it's very dense sometimes. If I was looking at basic derivative formulas just to kind of think about something here. No, it's so many words. Ugh. No. So like I'm looking at section 3.3 right now. Oh, which is I remember the other thing I want to show you. Yep. Which is not here. I'll add this in here in a second. Actually, let me do this right now while I'm thinking about it. Let me do something cool. I'm going to. No, that's not what I meant to do. There, I want to do that. So in case you don't have the book or don't have the book on you all the time, someone's calling me. It's likely a scam though. Do that. Do that. My other 17A co-class. Cool. Yes. That. Then we want the modules. Not all the modules, James. Just the textbook chapters. Cool. All right, we'll check it out in seconds. Yes. Yeah, reading the book seems terrible. I mean, not terrible. Like looking at section 3.3, I would look at like, okay, there's a rule there, and then I'm gonna look at the example. And that's why I was doing that, so I could show you. I was like, I know there's a reason I just did the thing I did. Modules. So now if you look in the modules and you go down to the bottom, oh my God, why are you open? Oh, there we go. Textbook chapters right there. So these are literally the chapters from your textbook. So if I click on this one here, then takes a moment, maybe more than a moment. There we go, chapter 3. So I was looking specifically at section 3.3 just because it seemed not too terrible. It's probably easier just to download it, but hey, I don't need to do that right now because I already have it downloaded. And take your time. Anyway, the point being that reading this seems like, oh my God, rates of change. Okay, blah, 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 blah. Instantaneous, okay, sure. They're talking about it. So I would maybe focus on the boxes and then kind of look around. Like, okay, well, what if that doesn't make sense to me? Maybe go back and read some of the words that they're saying about it. I'm sure most of your teachers would love it if you read the textbook before you came to class. Some of them might even expect you to do it, or at least say they expect you to do it. It's probably a good thing to do. Does it work for everybody? Probably not. just because, I don't know, I feel like math textbooks are not always written like they're addressing the student. Like I read these textbooks sometimes and I'm like, what are they saying? So it's, yeah, I mean, again, my answers are never specific, right? I'm like, well, you could do this, this, and this. So I think if it makes sense for you to do it, you should. I think it's a good tool to try to do. If you get stuck somewhere, you can come ask me, you can come ask someone else. I'm happy to talk about it with you. Like, what are they saying here? Ideally, you would be learning a lot of what's happening in the textbook during the lecture that your instructor is providing. But some lecturers are better than others. Some lecturers are worse than others, and some people are not as good at making the math understandable as others. So it's on you kind of to make sure that you are getting enough instruction in whatever way you need. That's why you're here, so that you are understanding what's happening in your class. So there's my very long answer to your very short question. Other questions? I have a question. What do you have questions about mathematically? Like, what have you done in your classes so far that you're kind of like, I would like to hear more about that? I have a few ideas, but if there's anything that really sticks out to people, I would love to know. So here, personally, I'm thinking of things like, what is a function? What is domain, range, inverse functions, piecewise functions, things like that. That's kind of what I'm imagining I might talk about for the next, what, 48 minutes, 47 minutes? But if you have, yeah. Okay. Okay.
I was like in one of the first pages, and it was the mass of the tubular bone is.
Oh, all right.
And I was like, that has never. I don't.
It's a lot of words.
Yeah, I don't think that has ever been in any of my AP calc ones, and I like.
Is this from the textbook?
Yeah.
Cool, I've got the book. Let me take a look. And is it from section what? 1.1? All right. Math of the tubular bone. Great.
And
I'll
it was the.
Let me take a look here real quick while I get all this set up here. So one of the things I'll say about every math class really is a lot of the time it's as much an exercise in reading comprehension as it is in doing mathematics. So half the battle, a lot of the time, is the ability to read the question and understand what they're asking you to actually do. And I'm actually trying to find the question now. Would you know which number it was?
Example 6.
Oh, oh, cool. Right on. Example 6. Oh, yes, I see a giant bone right here. Bone mass. No, that's, Is it example 6? Oh, yeah, there we go. I see. Okay, cool. Yeah, we can take a look at that one. Let me grab things here. Let's move this over here so you can all see things. Oh my God, James, come on. A couple things as far as how this typically goes. I'm gonna write things here so you can see them. Well, here so you can see them, which actually brings me to my first point. If I'm writing something and you can't see it because I've gone down here, let me know, please. It'll happen often. So just say, hey, James, we can't see. Please move your paper. The other thing is if I write something that may not 100% be clear, might be illegible, you're not sure if it's a 3 or a 5, I'm not sure if it's a 3 or a 5, just ask. I'm happy to clarify. I will try my absolute best to write things as clearly as possible, but sometimes I get going kind of fast. And then things start to look a little bit shaky. So don't hesitate to say, I need some clarification on that. Let's look at this. So section 1.1. So the thing about the first couple sections in the calculus textbook is they're usually trying to do like all of pre-calculus in a few sections. So this first section is what, 4 ways to represent a function. interesting. What 4 ways? That's annoying. Sure. There is, I mean, okay, there are some good. I can think of 2 specifically that I would use. Typically, like the f of x equals whatever, x squared plus 7x, or the graph of it. Those are the kind of 2 ways I think about representing a function. You can also make like a table, I guess, with inputs and outputs. I feel like they say 4 ways, but do they actually like enumerate the ways here? Not really. Okay, that's fine. So let's look at this example because I think it's kind of worthwhile. Let me write some things down here. So we are Co-17A. This is the afternoon class. And today is the 26th of September. Cool. And this is section 1.1, example number 6. So I'm going to read the question. Bone mass. A human femur thigh bone is essentially a hollow tube filled with yellow marrow. See figure 13. In case you. There it is. Can you see that all right? Kind of. Okay, can you see that all right? Oh yeah, it's hard for me to see from over there if you can see over there. If the outer radius is r and the inner radius is r in, an important quantity characterizing such bones is k equals the inner radius divided by the outer radius. What's k? They haven't told us yet. The density of bone is approximately 1.8 grams per cubic centimeter, and that of marrow is about 1 gram per cubic centimeter. For a femur with length L, express its mass as a function of K. All right, so what do they want? They want the mass as a function of K. What do we know? We know that K is equal to the inner radius divided by the outer radius. We also know that the inner part, which is the marrow, I think I could probably draw a picture here. The picture might be good. So the idea, I think, is kind of like we've got this tubular shape, which is representing like the bone. And then we've got the inner part, which is where the marrow is. I go for some bone marrow. Sounds kind of good. Have you ever had bone marrow? I mean, it's very rich, but it's pretty tasty if done well. Kind of weird though. So the inner tube there is where the bone marrow is. The outer tube there is where the bone is. Right, the bone? Yeah, sure. So this is the inner radius. And what's a different color, James? This is the outer radius. So first, let's just find the mass of the whole thing. So the mass, if you're talking about volume and density, I always remember, what's it, DMV? The density is the mass divided by the volume. So I'm trying to find the mass. That means the mass is going to equal the density times the volume. All right, so for cylinders, there's a lot going on in this problem. Okay, so let's talk about the inner cylinder first. So the inner cylinder, the volume is going to be, well, the volume of a cylinder is pi, well, let's just draw it. So if the volume of a cylinder, if the radius is r and the height is h, the volume is the base area, which is just the area of a circle, which is pi r squared, times the total height, which is h. Oh, I guess they said the femur had a length of L. Sorry about that. So the volume of the inner cylinder is pi inner radius squared times the length of the femur. And then the mass is going to be that volume multiplied by the density. And I didn't write down the densities because I'm a fool. The density of the marrow, which is the inner part, is 1 gram per cubic centimeter. The density of the outer part is 1.8 grams per cubic centimeter. Should not include an M in your gram. That's terrible notation, James. Gram is G, not GM. So the mass of the marrow, the inner cylinder, is pi times the inner radius squared times the length times the density, which is 1 gram per cubic centimeter. At this moment, I would do some dimensional analysis to make sure my units made sense. So check this out for a second. Assuming the radius and the length are measured in centimeters, which would be sensible. I mean, you can measure them you measure them in meters or miles, but it's a length unit, and I'm going to use centimeters, so that's what we're using. I have centimeters times another centimeter times grams per cubic centimeters. The cubic centimeters are going to cancel. I'm going to be left with grams, which is good because I'm trying to measure a mass. So the units are looking nice. I'm happy with this. So there's the mass of the inner part. Now I want to find the mass of the outer part. So I need to find the volume of the outer part. So the volume of the bone. So it's the volume of the entire cylinder minus the volume of the inner cylinder. So that's going to be, well, the outer cylinder, the entire cylinder has a radius of r. That's going to be pi times regular r squared times the length. And then we're going to have to subtract the inner cylinder's volume, which is pi times the inner radius squared times the length. And if we want to get the mass, we're just going to multiply that by the density. That's a little low there. So the mass of the bone, watch here, I'm going to do a little bit of simplifying. I'm going to factor out the pi and the L from both of these terms because I can. And often we choose to factor it when we can. Oh, that's interesting. And then we're going to multiply that volume by the density, which is 1.8 grams per cubic centimeter. And again, I'm confident that the units are all right because this here is measured in centimeters times centimeters squared, which is centimeters cubed. Centimeters cubed cancel the centimeters cubed. I know they're not written in there, but we'll just pretend like they are. 3.8 grams. Okay, so the total mass is going to be this mass plus this mass. I'm not going to write the units this time. I'm just going to say it's pi times r inner r squared times L plus this one, which is pi times, I'm going to write this part first, outer r squared minus inner r squared times L times 1.8. Did we answer the question? Are we done? Let's go back and read the question. We want the mass as a function of K. There are no K's in my answer. It's a problem. We gotta make that work. So we know that K is equal to the inner radius divided by the outer radius. Oh, thank you. Curious here. How's that gonna work? So let me make sure. Yeah, I've got the same thing they've got. Yeah, that looks right. Cool. Okay, so here's what they've decided to do. They've decided to replace, okay, I see. So I feel like this question is not, let me read it again just to make explicitly sure. No, it's not. I would say this question is not 100% clear, but that's fine. So we're gonna solve or isolate the inner radius and say k times the outer radius is equal to the inner radius. And we're gonna replace each inner radius with k times the outer radius. Here's what we've got. We've got the mass equal to I times kr squared times L plus pi times r squared minus kr squared times L times 1.8. And technically this is correct. We could probably simplify it more. We probably don't really need to, but you could. I don't think we need to. So yeah, it's kind of a gross question. It's a lot of pieces in there, a lot of having to read and identify what they're really asking for. This is maybe more than I would say most questions would usually like make you come up with on your own, but not completely. So this is not an unreasonable question to ask. It's certainly one of the longer word problems, but not out of the world. You're welcome. So it's a good example of a word problem. And this class, I will say, does have a fair amount of word problems where you have to kind of discern what's going on and what they're asking for and what things mean. And you can kind of, if you look in the book, you'll see in every section, especially section 1.1, there's a lot of word problems. You can see all things. Yes, if people need to leave early for whatever reason, that is totally fine. Or just need to use the restroom, also totally. You don't need to check in with me. You can go use the restroom, you can come back, you can go to your other class if you have another class. I know that for some people, this class did conflict with another class completely or partly. So if there's another class you need to go to, totally fine. I will not be offended. I will not assume you just don't like hearing me. All right, let's talk a bit more about functions. And again, that said, if you have general questions or specific questions, you're always welcome to ask them. I'm really happy to go over examples that were confusing, unclear. But let's talk about functions a little bit more. So what is a function? Well, it's kind of a rule. The kind of defining feature of what makes a function is that each input gets assigned to only one output. So my kind of favorite example of a function is f of x equal to x squared. And no matter what number you pick for x, and you can pick any real number, you're only going to get one output for each choice of x. So if x equals 3, f of 3 is 3 squared, which is 9. Or if x equals 2, f of 2 is 2 squared, which is 4. Or if x equals 1, f of 1 is 1 squared, which is 1. Or if x equals 0, f of 0 is 0 squared, which is 0. Or if x equals -1, -1 squared is +1. And so on, right? You could literally do this forever. I'm only writing a very few, not a square there, James. I'm only writing a very few inputs. But the point here is that each input corresponds to only one output. It's perfectly okay that, see, look there, my 4 and my 9 kind of look the same. That's a 4, that's a 9. It's perfectly okay that the number 9 corresponds to 2 different inputs. But you couldn't say plug in 3 and get 2 different results. Or you could, but that wouldn't be a function. So this is a function, perfectly nice. This is one way of representing it, f of x equals x squared. You could also write it as y equals x squared. That'd be perfectly good as well. Or you could draw the graph. Looks like everyone's favorite parabola has the vertex at the origin. So you can think of the defining feature of a function as being the fact that each input corresponds to only one output. Another way to say that graphically is that this graph passes the vertical line test. Any vertical line I draw passes through at most 1 point on the graph. That's the same thing as saying, if you pick a value for x, you're only going to get one value for y, right? If this is the line, x equals 3, then that point is the point 3, 9. For the x value of 3, you're getting one y value of 9. And similarly, for the x value of, say, 2, you're getting a y value of 4. So that's why the vertical line test really does determine something's a function or not, because if it passes it, you're saying, oh yeah, each input only gets one output. Something else I want to say here. Nope, we're good. Okay. On the other hand, not everything is a function. And probably our favorite example of not function things, my favorite example anyway, is a circle. A little bit better. So for example, x squared plus y squared equal to 25 is not a function. And you can see this in a couple different ways. I should specify here, not a function of x. In the first quarter of calculus, we are typically always thinking of x as the independent variable that you're going to be a function of, and y is the dependent variable that is the function. So one way to see that is by trying to solve for y. I'm not even going to do that yet, though. I'm going to point out that here I could pick a value for x. Like, let's say we pick x equal to 3. And let's find the y value, because there's more than one. So I plug in 3, I'm going to have 3 squared plus y squared equals 25. 3 squared is 9, 25 minus 9 is 16. And what are the solutions to y squared equals 16? 4 is one of them, and -4 is the other one. So the problem here is that one x input corresponds to multiple y outputs, which is not so much a problem, just that it means it's not a function. So not a function. One x value corresponds to more than one y value. But it's kind of a pain just to pick an x value and try and find the y values that go with it. A better way to have done this would just say the word woo. Can I say the words? A better way to have done this would have been just to have solved for y or isolated y in the first place. If we're imagining that y is going to be a function of x, then we should just be able to write y equals some stuff with x's in it. So if I were going to do that, I would take my x squared plus y squared equal to 25, and I would solve for y. So y squared is going to equal 25 minus x squared. And then what should I do to both sides of this equation if I'm trying to solve or isolate y? You can just say words. It's totally okay. How do you undo a square? With a square root. Something the square root of both sides. Square root of y squared equals the square root of 25 minus x squared. Okay. So normally we kind of skip this and just get to the result, but I really want to talk about just for a brief moment why what's about to happen is going to happen. So let me ask you all a question. What's 5 squared? What's the square root of 25? Right, good, we're on the same page, cool. Okay, what's -5 squared? 25, what's the square root of 25? Right, 5. So, interestingly here, when you take the square root of something squared, whatever that something is, the end result is the corresponding positive value. If I were to plug in 5 for x, I would get 5 out. If I were to plug in -5 for x, I would still get +5 out. There's another function that does that, where if you plug in a positive number, you get the same positive number, or if you plug in a negative number, you get the corresponding positive number. What's that function called? The absolute value function. So it is literally true that the square root of x squared is the same as the absolute value of x. Which is also kind of a terrible pain. Because then when you're trying to solve something like this, you don't just get y over here. You get the absolute. Let me ask you all now a different question. If I was trying to solve the absolute value of x equal to 7, what's one solution? What could x equal? Sorry, I'm not very good at hearing. -7 is one answer. What's another answer? The obvious one, yes, 7. Oh, look, you get plus or minus 7. So when you have the absolute value of x equal to something, you're going to get x equal to plus or minus that something, essentially two different answers. And that's what's going on here. The square root of y squared is really the absolute value of y. And then when I solve this, I get y equal to plus or minus the square root of 25 minus x squared, which is two different things. So for example, if x were to be equal to 0, y would be equal to plus or minus, the square root of 25 minus 0, which is 5. One input is giving two different outputs. That means it's not a function. So whenever you're trying to, if you're ever trying to determine whether something is a function or is not a function, and you isolate y, if you get y equal to some plus or minus stuff here, it is almost assuredly not a function because you're getting two different y values corresponding to one x value. Lastly, and probably the nicest way to see that this isn't a function is to graph it. So we can also graph the function, not the function, the equation x squared plus y squared equal to 25, which is a circle. And it's a circle whose radius is 5 and whose center is 0, 0. So you get the points like 5, 0, 0, 5, and -5, 0, and 0, -5. You also get points like, sure, 3, 4, and 3, -4. Oh, look, that one x value is giving two different y outputs, and that's exactly the same as failing the vertical line test. Because there's a vertical line. What is that vertical line? Like, well, let me ask that question better. What is the equation of that vertical line that goes through the coordinate 3, 4, and 3, -4? Let me ask a better question, actually. Which coordinate stays the same or doesn't change? The x coordinate or the y coordinate? Right. So just make sure everyone's on the same page here. It's alphabetical, right? X comes before y. So the x coordinate is the first coordinate, the y coordinate is the second coordinate. The x coordinate doesn't change. What is the x coordinate equal to on this line all the time? Sorry, say that again. I really like, my hearing is not excellent. What is x equal to? Yeah, show me on your fingers. What is x equal to the entire time on that line? Yes, exactly. That's the equation of the line. X equals 3. So we have a vertical line, which is always x equals a number. And look, it's got two different points on the graph. It fails the vertical line test, not a function. Still a lovely equation. That's actually a good thing to know that if you ever have a line that goes through 2 points and one of the coordinates doesn't change, that means it's that coordinate equal to that number. So if you had another line that went through the points like, say, 5, 4, and -7, 4. The y coordinate is 4 on both of those. That means the equation of this line has to be y equals 4. There's no other option if it's a straight line. All right, let's see. It's 3:10, got 20 minutes. We should probably talk about domain. The other kind of most important thing you've probably talked about so far. I will say, kind of unfortunately, most of these calculus classes pretend like they want to talk about pre-calculus for a second, the assumption is really that you know pre-calculus. And they're going to cover it for about 2 or 3 days and be like, okay, there's all pre-calculus in 2 or 3 days. So if there are things that you need to refresh your memory on, you definitely should, because the class is going to move forward under the blanket assumption that you know how to do pre-calculus things, how to define domain and range and graph certain types of functions and lines and parabolas and other things, which we will certainly talk about in this class, but just be aware that all of your 17A instructors are going to kind of work on the premise that you know the pre-calculus things, you know how functions work. Well, let's talk about domain, because that's probably also one of the most important things that we talk about. So domain. I would say that there are typically 3 types of functions that have domain issues. Well, let's talk about one that doesn't. So f of x equal to x squared plus 4x plus 1. This function doesn't have any domain issue. X could be any real number, and we can plug that into that function and get a real result. So the domain here is all real numbers. Typically, when you're expressing a domain, I would say the default best way to do it is using interval notation. So you should write it as everything from negative infinity exclusive, because we never include infinity because it's not a real number, all the way to positive infinity exclusive. When your domain happens to be all real numbers, you could also, if you prefer, use the fancy R, which represents all real numbers. Let me give you an interesting example here. So most of the time, we just use what's called the natural domain of a function, where it's like, oh yeah, look at that function, what's x allowed to be? Occasionally, though, the context of the question might change what our domain is. So let's say now f of x equal to x squared plus 4x plus 1 is the mass of a, I'm going to make something up that's totally not true, of a rabbit that is x centimeters tall. Does it make sense now for x to be any possible real number? What kind of numbers don't make sense? Negative numbers don't make any sense at all. 0 probably doesn't make sense either, actually, to be honest, because if a rabbit is born, it's typically not going to be 0 centimeters tall. So here, I would say that the domain, there's probably some like shortest rabbit on record, but let's just cover our bases here. The domain here should be something like 0 to infinity, exclusive of 0, not including 0. And probably more realistically, like, I don't know, 5 centimeters, 5, but okay, fine. So sometimes there's a domain that, even though technically x could be any real number here, since the function is specifying something about a physical thing in the world, we should take that into account when we're talking about the domain. That will come up occasionally in some of these word problems, where something's a lot of times not being negative because you're measuring a length or a volume or something that just, right, as a physical object that can't have a negative quantity. But there are other things as well that will come up to be like, oh yeah, it doesn't, or sometimes it makes sense, like you were talking about, like the number of items sold, the domain might be all positive integer numbers because you can't sell a half a thing. So something to be aware of. But most of the time we talk about domain in the other sense. We're just like, what is the independent input variable allowed to be or not allowed to be? So an example would be something like, find the domain of f of x equal to 3x minus 6 over x squared minus 5x minus 20. And here, unlike the previous example, we have a fraction, we have a rational expression, and it is not okay to accidentally divide by 0. Right? Division by 0 is undefined. So we have to make sure that we exclude any value of x that makes the denominator such that x squared minus 5x minus 24 is equal to 0. So then we solve this equation, typically by factoring. Here I'm going to factor, I'm going to get x minus 8 times x plus 3. Negative 8 times 3 is negative 24. Negative 8 plus 3 is negative 5. So that checks out. That is how that factors. And so then we want to make sure we exclude x equal to 8 and x equal to negative 3. I like to draw it on the number line. I find it helpful. So if I'm looking at the number line, the only things I don't want are the 8 and the negative 3. So there's 8. There's negative 3. Do you make sure that when you're writing this on the number line, the bigger positive numbers are to the right, the smaller positive numbers are to the left, the smaller negative numbers are to the left of that, the bigger negative numbers are to the left of that. So really negative, slightly negative, 0, slightly positive, really positive. And then we don't want 8. We don't want negative 3, but we do want everything else. So our domain is literally every real number except for negative 3 and positive 8. So writing that out using interval notation, we want everything from negative infinity to negative 3, exclusive of negative 3. Union, everything from negative 3 exclusive to positive 8 exclusive. Union, everything from positive 8 exclusive to infinity exclusive. That's the domain. Everything except for negative 3 and positive 8. So one type of function that has domain restrictions is when you have a denominator that can equal 0. I should be extra explicit here. Not every fractional thing is going to have a domain restriction. For example, if I asked for the domain, thank you, of g of x equal to 3x over x squared plus 25, you can start off the same way and say, okay, well, I want to make sure I exclude x squared plus 25 equal to 0. But that equation has no real solutions. Because x squared is always bigger than or equal to 0. And if you add 25, it's always bigger than or equal to 25. If you try to solve it, you get x squared equal to negative 25. And if you take the square root of both sides, you get x equal to plus or minus the square root of negative 25. And although that is a thing in the world, it's an imaginary number. And when we're talking about the domain of functions, we're talking about real valued functions. So the outputs have to be real and the inputs also have to be real. So this is plus or minus 5i, and we don't want any imaginary numbers. So here, the domain is all real numbers. Negative infinity to infinity. When we talk about functions, the always implied word that's not said is it's a real value function. Every time you plug in a number, the output has to be a real number. The reason that's important is because of the next example. So we don't want division by 0. We also don't want to be taking square roots or any even roots of any negative numbers. So for example, if my function was f of x equal to the square root of, sure, let's do that one, x squared minus 36. Yeah, I like that number, sure. My argument of my square root, the stuff inside the square root, the argument, which in this case is x squared minus 36, must be greater than or equal to 0. Or in other words, it must be non-negative. I don't know if this is supposed to be a dash there or not. I don't care. It's not a spelling, hyphenation, punctuation class. It's a math class. So non-negative, fine how it is. So that means we're going to set the argument of our square root or any even root to be greater than or equal to 0. And I want to be very, very explicit here. Any even root. So if I had x squared minus 36 to the square root of that, 4th root of that, 10th root of that, 12th root of that, 82nd root of that, any even root means the domain, the stuff inside that root has to be non-negative. It's also true if you've written it as a fractional power. So I could say the same thing would be true if I had, say, g of x equal to x squared minus 36 to the 1/12th power. That's the same as the 12th root. It's an even root. The argument has to be non-negative. Okay, so we're going to solve this inequality. And if your inequality is non-linear, meaning you have powers of x other than 1, we really should solve it by leaving everything on one side, 0 on the other side, and factoring as much as possible. Technically, with this one, you could probably bring the 36 to the other side, square root both sides, use an absolute value, but it's safer just to factor. Especially because the next example, you're not going to be able to do the thing I just said. So let's try factoring. This factors as x minus 6 times x plus 6 greater than or equal to 0. I'm going to put the numbers, or I should say the zeros of that left-hand side expression on the number line. So if I let x equal 6, this part's 0. If I let x equal negative 6, that part's going to be 0. And the reason I'm focusing on the zeros here is because for an expression to be to change from being positive to negative or negative to positive, what number does it have to go through? 0. Technically, you can also go through being undefined, but this function is not undefined, so it's fine. But right, we have to go through 0. So I know that everywhere to the right of 6, this expression is either always positive or always negative. So let's test 1 point. I'm going to test 7, which is boring, but fine. If I plug in 7, 7 minus 6, I don't care about the number, I care about the sign. 7 minus 6 is positive. 7 plus 6 is also positive. And a positive times a positive is positive. I could have picked 7, I could have picked 70 million, and the result would have been the same. On the other side of 6, between negative 6 and 6, if I'm between a negative number and a positive number, I like to always pick 0. Seems like the best choice. It's usually easy to plug in. If I plug in 0, 0 minus 6 is negative, 0 plus 6 is positive, and a negative times a positive is negative. Finally, pick something way over on the left side, like negative 10, just for fun. Negative 10 minus 6 is even more negative, so it's negative. Negative 10 plus 6 is also negative, and a negative times a negative is positive. Negative times a negative is positive. If you have an even number of negatives multiplied together, the result is positive. If you have an odd number of negatives multiplied together, the result is negative. And since we have 2 negatives multiplied together, that's an even number, that's a positive result. Which parts do we want? We want the positive parts or the negative parts? Right, because this inequality says greater than or equal to 0. So not only do we want the positive parts, we also want the parts, specifically negative 6 and positive 6, to make it equal to 0. So we want all of this, none of this, and all of this. So here our domain would be everything from negative infinity to negative 6, inclusive with a bracket to include the negative 6, union, bracket to include the positive 6, to infinity. Infinities always get parentheses again because they're not real numbers. We can't actually include them. All right, I should give you one more example because there's one more type of function that has a domain issue. So domain issues are functions that either have fractions, have even roots, or thirdly, logarithms. So domain sure, f of x equal to the log base 2 of negative x squared plus 5x plus 6. And so I'll point out, because it is worth pointing out here, and how much time do we got? I got 5 minutes. Okay. So if you were to graph f of x equal to the natural log of x. Why the natural log or log base e? Because it's the most typical one. It's the natural base for a reason. It's the best. Its derivative is the nicest. We'll talk about more later. But it looks like this. Got an intercept at 1, 0. It's got a vertical asymptote at the y-axis. So you can't plug in 0. If you plug in really, really small numbers, the output gets very, very negative. but you can't plug in 0. It's undefined. It's kind of the only function that's undefined in a way that's not just division by 0. Right? Most everything else, if you plug in something, it's undefined because somehow you end up dividing by 0. Except for the logarithm. Logarithm, you're really not dividing by 0. And I don't have, we'll get into why that's true next time. I will point out my hand's not the best for it, but your younger hands with less lines on them. You look at your right hand, you can kind of see a natural log function right there. And you can kind of see an e to the x function right there. Make sure you're looking at your right hand, your right hand, right hand. Kind of cool. So you got a cheat sheet right there all the time. Your left hand has some other functions we'll talk about later, which are almost the same. So the whole point is that the argument of f of x equal to log base 2 of negative x squared plus 5x plus 6. The argument is the inside part. And it must be positive. Not just non-negative, but positive. It has to be greater than 0. It cannot equal 0. Because we can't take any log of 0 and we can't take any log of a negative number. And I say any log meaning a log with any base. Log base 2, base 3, base 10, base whatever. You can't take log base whatever of negative numbers or 0. Undefined. So that means we're going to have a very similar inequality as last time. Just like with the square root of some stuff, the stuff had to be greater than or equal to 0. Here, with a logarithm of some stuff, we need to set the inside stuff, the argument, to be greater than 0, strictly. Not including equal to 0. A couple ways to solve this. I really want to factor it, but I really don't like factoring when I have a negative on my leading coefficient. So I would much rather multiply both sides by -1 to have a positive x squared. So I'm going to say positive x squared minus 5x minus 6 is less than -1 times 0, which is still 0. I just multiply both sides by -1, and since it's an inequality, I had to change the order of the inequality. Alternatively, if you'd wanted to, you could have just added all this stuff to the other side and said 0 is bigger than positive x squared minus 5x minus 6. And that's exactly the same thing. It looks a little bit different. Either way, it's totally fine. I probably would prefer this just because I sometimes forget to change the direction of the inequality. So I think it's safer to add stuff to the other side so you don't have to multiply by negative. But either way, it's fine. As long as you're perfect. All right, let's factor this thing. This factors as x minus 6 times x plus 1 less than 0. We're going to find the zeros of the left-hand side, which are positive 6 and -1. Put those on the number line. And then do the same kind of thing we did last time. Test a point in each of the 1, 2, 3 sections we have. To test a number bigger than 6, like 7 or 70 or 700. Whichever one you pick, that number minus 6 is positive. That number plus 1 is positive. And a positive times a positive is positive. We don't want 6 because if you plug in 6, you get 0 times 7, which is 0. And 0 isn't less than 0. It's equal to 0. And it's not a less than or equal to, it's a strict less than. Between -1 and 6, I would pick 0. 0 minus 6 is negative. 0 plus 1 is positive. And then negative times a positive is negative. Thirdly, pick a number less than -1, like -3. -3 minus 6 is -9. -3 plus 1 is a negative number as well. And a negative times a negative is, thank you, positive. I don't want the -1. Okay, be extra careful when you answer this next question. Actually, give me some thumbs. Thumbs up for yes, or thumbs up for positive, thumbs down for negative. Do I want the positive parts or do I want the negative parts? Thumbs, I want to see some thumbs. Thumbs, show me your thumbs, show me your thumbs. So, and yeah, you can do middle if you're not sure. It is the negative ones. So even though we started off by saying the inside stuff had to be positive, greater than 0, we changed the inequality and said the opposite of the inside stuff needs to be negative. So this is telling us where the opposite of the inside stuff is negative. So this region right here is where that stuff is going to be positive. Let's pick a number. Let's plug in x equal to 2. We plug in 2, we get -2 squared. I'm plugging it into right here. We're going to get -2 squared plus 5 times 2 plus 6. Okay, Here's another tricky question. What is -2 squared? -4. The x1 is happening first there because there isn't a parentheses. So we have -4 plus 10 plus 6, which I don't really care, but it's equal to 12, which is positive. So picking a number in between -1 and 6 makes the original thing positive. It also makes this thing negative, which is totally fine. So our domain here is everything between -1 and 6, not including the ends. So it's parentheses -1 to +6. So 3 domain issues that can occur when you either have division by 0, the square root of a negative, or the logarithm of a negative or 0. So those are the 3 domain restrictions we have to look out for. Technically, there's a weird fourth function that rarely comes up that we won't probably talk about, but I might mention a little bit later. But these are the 3. If someone asks you to find the domain of a thing, you ask yourself, are there any of these 3 things? And if there aren't, you're good to go. It's everything. If there is, you have to look at that. All right, I should stop talking. 3:32.